this is summarizing some of what we've done and then taking it a couple steps farther. So we're looking at vectors, linear operators, and inner product. So we have seen these things before. So I'm going to start with arrows, vectors as arrows, and we generalize from one, do them as a column, to n components. And we can also write them like this. Okay. This I haven't been doing, but we can write them like this, and this will take us into the standard formalism. Of course, you guys in 115 have seen this. Okay. And AI, BI, etc. are complex numbers. So those are the vectors. Here was B1 to Bn. Okay. I'm writing them as columns. And there's the arrow. I can write it like that. So then you generalize the magnitude. So the magnitude of a vector that we had like that is going to generalize to sum of AI star of AI, because it has to be real and positive. I equals 1 to n square root. So we have done this as well. Or with the new nomenclature, the magnitude of this vector A. Okay. Same. AI star AI square root. So that was the first step. Then we have the dot product when we started out with our arrows, and that's the inner product in general. And A dot B, through the arrows we had A sub I star B sub I. And that generalizes to A, B equals sum over A sub I star B sub I. So that's how we're generalizing. We have to make sure we take into account these are complex numbers. So that's the inner product. And if you have orthogonal vectors, that just means, in this more general case, orthogonal, meant 90 degrees between them. When we have the arrows here, we're just saying that A, B equals 0. Okay, so those are orthogonal complex vectors. So for the inner product, we have the important defining properties, which I'll just list here as well. So we'll call our vectors A, B, C, and then, so the vectors, and then alpha, beta, gamma are numbers. So then the inner product satisfies these properties. You reverse the order. It's the complex conjugate. So if you reverse the order of it, you have the original one complex conjugated. You have A and A greater than or equal to 0, and it's only equal to 0 if this is a 0 vector. Equal to 0 if A equals 0. And then you have linearity in the right side of the inner product. We'll squeeze that in right here. So you have A, beta, B plus gamma, C if you're in the second argument, so that would be beta AB plus gamma AC. So those properties defined in inner product. Okay. And you know, they're true back when we just had arrows in free space as well. So far, so good. Okay, linear operators. So that was vectors in the inner product. So now the linear operators. When we were just working with arrows in free space, we had matrices, but those properties also generalize. So let's write here linear operators. So first of all, we're looking at matrices. And let P be an n by n matrix. So the elements could be complex numbers. They could be real, they could be complex, depends. Okay. So then, with our vectors, we have A. So you operate this matrix on a vector and you get another vector, and that would be T11 to T1n to Tn1 Tnn, operating on this vector A1 to An. Okay. And so that's just a matrix multiplication. So the ith component of the left side is row times column, so it would be P I J A J, J equals 1 to n. So when we have matrices, those are linear operators. And we actually showed the linearity of this operation here. If we were doing, so we've done that before, T of A plus B. In fact, in the summation formulas, I'll go ahead and write T of alpha A plus beta B. You can easily show alpha BA plus beta PB. You do that in the summation formalism, so you know that it's linear. Okay, that's the defining property of the linearity. So then we have this, and now we can introduce the eigenvector and eigenvalue problem, which we did a couple on the homework. One good one. So eigenvectors and eigenvalues. So now we're looking at this equation here, except we have T A equals lambda A. So that's in general, T A equals lambda A. So the linear operator applied to a vector is equal to some number, some scalar times that same vector. For matrices that we have here on the left, we would have T I J A J summation equals, that's the I, equals to lambda AI. And the way to turn both sides into a summation is to say that's going to be lambda outside sum over j lambda aj delta ij, and that picks off this one here, but now we can have them both under a sum. And then we sum over t ij minus lambda delta ij aj equals 0. J equals 1 to n. And of course there are n of these, so I equals 1 to n on these as well. Good. So then you have a system of equations and you have to solve them. And the key to solving these is that to find the eigenvalues first, you have determinant of p ij minus lambda delta ij. Determinant of this square matrix equals 0. Then you can find lambda sub I equals 1 to n. So that's the process here. You've got the eigenvalue, eigenvector problem, solve this, and having found the lambda sub i's, then use the set of eigenvalues to find corresponding eigenvectors. And you find those by taking the known lambdas back into this equation, and then you can find vectors. Good. So first of all, these were three-dimensional vectors called arrows, and then we generalized them to complex arrays of numbers. Okay, so n-dimensional spaces. And the generalization of all these rules is then to functions in function spaces. So what we find with function spaces is that we find all of these same properties and rules, linear operators, etc. So that's what I'm going to set up now. And this was that homework problem. I did a smaller one in class, 2 by 2, and then we have a 3 by 3 matrix that we did on the homework. So that's where we followed all these procedures, and we even found the eigenvectors. And the eigenvectors happen to be orthogonal for our example, right? Our 3 by 3. Why were they orthogonal? That's just an amazing coincidence. So the orthogonality that we found in our homework problem is a problem of a certain type of operator. In this case, we have a real symmetric matrix that'll have the orthogonal eigenvectors, and we'll generalize that. But the eigenvectors don't have to be orthogonal. That's a special kind of operator. Our homework problem just happens to be of that type. So vector properties extended to functions. So that's our next topic here. And we did this a while ago, so it's nice to review what we had there. So let f, g, h be complex valued functions. Functions of a real variable. So that's what we're working with now. And they're of a real variable, but this would only be one part of it. Right? You could have a real and an imaginary part. But that's the idea, a real variable x. And then imagine this is a set of all such functions, say on A to B, and then this set satisfies the vector space axioms. it satisfies a function, defined, well-defined, satisfies the same axioms that arrows did originally, vectors did. So you have H equals F plus G equals G plus F, etc. Commutativity, associativity, and so forth. Now, if we're going to let the function be a vector, so we've got the vector, which we'll call F, that is the function F of x. So if we just want to label it, it's called vector F in that form. And then we have that inner product. So the inner product looks like this. So F and then FG. So the inner product of F and G is then the integral F star of x, G of x, dx from A to B. And the inner product defined like this has the properties that I just erased. It has all the properties of the inner product for arrows, for vectors, and it has those three properties. Okay, so you can check that off. You have an inner product, and in particular, you can have two functions that are orthogonal to each other, simply because their integral is defined like this, turns out to be 0. So I'm just going to write here, satisfies the previous definition. And I could put the, do I have that? Yep. So the norm is this object here, the norm of, say, F, so with those two lines, is equal to the inner product with itself, square root, and that generalizes the magnitude. Magnitude of a vector that we have been using before. So when you have that, and right, it's just a direct generalization, now you can normalize a function. So normalized function, or normalized vector, right, which is what we have there, is just if you take F and F with itself, scalar product, so that's the norm squared, and you set it equal to 1. So F star of x, F of x dx, A to B equals 1. So then you've got a unit vector. If you just impose this on the thing, you've got a unit vector. And if you have a set of such unit vectors, and they're orthogonal to each other, you have what's called an orthonormal set of vectors. So, normalized function, so a set of functions set of functions f sub n of x is what we call orthonormal. If they're all normalized and orthogonal. So if f sub n, f sub n, so if this whole set of inner products is just equal to delta n, right? Bound for delta 1 n equals n 0, n is not equal to n. So we originally had that with I hat, j hat, and k hat, right? In the world of three-dimensional arrows. And we have it with, as we'll see in a minute, we've seen before, with infinite dimensional spaces as well. So I've got the normalized function, I've got the orthonormal set, and then if you can expand any function in terms of this set, then we would say it's a complete set. Okay? And again, this is just a generalization of what we had with I hat, J hat, and K hat originally. So these are all important definitions and terminology. So a set of functions is complete if any function in the space can be expanded in terms of those. Linear combination, so we would be, in this terminology here, we'd be saying this vector can be expanded as C sub n Fn, and then overall possible n. So that's a linear combination. And if any function can be done like that, we say the set is complete. Okay, the set of functions is complete. Go back to I hat, J hat, K hat. Real vectors in 3 space. What about that? Are they complete? I hat, J hat, and K hat. 3-dimensional space, 3 orthogonal vectors, and any point in space we can do A I hat, B J, and so on. Okay. So for I hat, J hat, and K hat, it's complete, and for this infinite dimensional function space, it'll complete if any function can be expanded that way. Now there are fine points because the functions are defined in a certain way. They're continuous, they're differentiable, they're continuously differentiable. So those definitions, when you're doing functional analysis, you got to pay a lot more attention to them. But for well-behaved functions that you draw on a page, we don't have to worry about the fine points. Okay. So we've got that, and then for the coefficients. So what are these C sub n? Well, what we do is we multiply f sub m on the left, f, and now we have a sum of f sub m, c sub n, f sub n, like that. Now, since we're on the right side of the scalar product, we can pull that C sub n out, and we've got f sub m, f sub n, that's the scalar product. And this, of course, is the Kronecker delta. We have sum over C sub n, delta mn over n. And that just picks off the one and only so that's how the coefficients are obtained. Multiply from the left with the m function, and that's because these are orthogonal set. So this too is a property that you would have had with your I hat, J hat, K hat. Good. So to make this concrete, we go to our Fourier series, and then we'll do that little calculation we have on Tuesday. Put that into the full context here. So, example, Fourier series. Here's what we're going to, here's how we're going to look at that. So this takes us back to when we first learned this we had c sub k e to the I kx to the Fourier series. K was an integer, c sub k was 1 over 2 pi minus pi to pi f of x e to the minus I kx dx. So what we're going to do is put this into slightly more general form. Now what we're going to do is consider functions from 0 to 2 pi into the complex numbers. Remember, these were for minus pi to pi, but the properties we studied for this set of, for these functions are actually all inherited for the identical for 0 to 2 pi, okay? So we'll do them for 0 to 2 pi because we have a nice application going on that. But what we'll do this time is define our vector e sub k as e to the I kx divided by root 2 pi. That's just going to take care of the 2 pi in this calculation here. Okay. Yeah. So this, as defined like this, is a unit vector. Because it's got, when you square it, you're getting the 1 over 2 pi in there, and then you integrate it up. So then we have f g as before, but without the 1 over 2 pi. So f g is just f star of x, g of x dx. So that's just a equivalent convenient thing to not have the 1 over 2 pi floating around. It's been built into the basis functions. And so now if you have f equals sum over c sub k ek like that, it's really the same as this, with a slight shift in definition on the e sub k. Then, so I'm just going to repeat what I have over there. Then e sub m f scalar product is going to be the sum over, same step I did over there, c sub k e sub m e sub k summing over k. Now these two have that Kronecker delta property because each one has 1 over root 2 pi. So when you multiply them together, you get the 1 over 2 pi, and the integral turns into, so that's Kronecker delta. So as defined, those are orthonormal delta mk equals c sub m. So exactly the same as we had before. Let's see what else we need for that. Oh, and this one, since we know where this came from, minus infinity to plus infinity, this one is explicitly infinite dimensional. So I'll just put your note, infinite dimensional. Dimensional space. So yeah, it's important to know where that comes from, so you don't start visualizing, infinite dimensions. Right, it's a normal function, but the property of expanding it like this gives us the infinite dimension. Good. So far so good. Okay, so next, that we have these vector spaces and expansions and so forth, we want to talk about the linear operators. And here I can repeat the one I did last time, fully example I gave last time, so we're going to use the same space of functions that we had before, 0 to 2 pi. Let us consider 2 pi periodic functions. So those are, they're on 0 to 2 pi, call that the phi axis, and then they repeat themselves. Okay, so we've got 2 pi periodic functions, and the operator we saw last time, we're going to call it q hat equals pi d phi. And we're operating on functions FGH. So I d phi of alpha f of phi plus beta g of phi. Because differentiation is linear, so we end up with alpha I d phi f plus beta I g, and that's alpha. Well, this was q hat. So yeah, this equals alpha q hat f plus beta q hat. That's the same property we had with the matrix multiplication. And what if this were a second derivative? Would it still be linear? Or a third derivative for that matter? It would still be linear because we would just say 2 derivatives, 3 derivatives, right? Those are the laws of differentiation that you can pull a constant through. So a second derivative would also be, I'll put that as a note here. Second derivative also linear. What if the operator were multiplication by another function? Actually, let's talk about that. I don't think I have that note here, but it's important. Okay, we'll give it another name. We'll call it p hat. So, question is p hat equal p of x linear? Is that a linear operator? And we just go to our defining figure. What we have to say is p hat of alpha f plus beta g is equal to alpha p hat f plus beta p hat operating on g. See, that would be the defining property of linearity. And f, you know, f and g are functions of x, right? And yeah, in fact, this multiplying by a function is just a common factor, so it pulls through. Okay. So that was the question, and the answer is yes. Okay. So, yes, okay. It is. So that's linear as well. We can make use of that fact later on. So good, we've got, but we're back to q hat here. So now q hat f equals, or should I write it? Yeah, let me write it with this notation. Q hat f equals lambda f. So Q hat is a linear operator, so that's a eigenvalue, eigenvector equation. So we'll just mark all these. This was our linear operator. This is our vector. find such a vector that satisfies this differential equation, then that's the eigenvector. And there's its definition. So yeah, we did this last time, but we'll look at it again. So now we have I, B, E, phi, f of phi is equal to lambda f of phi. When we actually get down to solving this, multiply both sides by minus I, get D, E phi, f of phi is equal to minus I lambda f of phi. And then we had this last time as well. F of phi is some constant, e to the I lambda phi. Minus, in this case, minus I lambda phi. Brings that down. And in order to have a 2-pi periodic function, this lambda can't just be any number, right? Here it can actually be any complex number, but it actually has to be a real integer. It has to be an integer. Then f of phi equals f of phi plus 2 pi tells us that lambda equals k element of not c, but element z, the integers. And now we have our Fourier series back again. Okay. So this was the defining, you can say this is a defining differential equation for those Fourier series, not the other one. Pick up the integers. Anything else? Good. So we did that last time, and I'll just note that these functions now, so now, actually let's go ahead and fill that in. Now, we can let, f of phi be this, e to the I k phi over root 2 pi. We can choose it, because that's the normalized one. It's the normalized eigenvector. And at this point, I would have put a little k here, a little k subscript. And in fact, I'll call it the normalized set of eigenfunctions, of eigenvectors. This is the all-time example too, because it's the simplest one. I want to get, and I have a few minutes, I want to show the much more complicated one. Let's see how we can get there. Good. So eigenvector equation, this example we did last time as well, takes us right to our Fourier series. So now let's see if we can talk about what you find in quantum mechanics. Very briefly. So, in quantum mechanics, we use these formalisms. So, I'll just list a couple of things. Physical state is represented by a wave function that's normalized to c of x squared dx equals 1. Okay. Observables those are operators. Q hat, let's call them Q hat, like we've done operator before. write it like this, C Q hat C. Going to write a couple of more definitions. The expectation value, that's the outcome of an experiment, and it has to be real. So Q must be real. And what does that mean here? So in this symbolic thing, Q hat C has to be equal to two steps here. It has to be equal to its own complex conjugate. Complex conjugate. But remember, when you complex conjugate this, you can reverse the order, so that equals Q hat C like that. So it has to be real, so you complex conjugate that. And that means that this very property means that Q hat is a permission operator. So now you have some added properties of your operators. That little D over dp one that we have was also permission. But I'm just going to list the properties here. So if you have such an operator that has these properties, it has orthogonal eigenfunctions. Permission operators have orthogonal eigenfunctions. And that's really nice, because if you can find one of those sets, then you would have the eigenvector eigenvalue, I'm going to call them Q. You'd have the eigenvector eigenvalue equation. Okay? So you'd have this operator. We've seen our simple Q hat, it's a differential operator. You'd have an operator eigenvector equation. And then if you found the solutions to this, so let's just call this eigenvector eigenvalue equation, or eigenvector equation eigenvalue. So if you found those, then you'd be able to say C is equal to the sum of, I'll have to give it some name, sum of alpha sub I, C sub I, right? That would be the form that you would end up getting, just the way we did with the I hat, J hat, K hat to begin with. Okay, so we don't have time to run through all these. You'll learn that in quantum. But I have a minute. I do want to put the Schrödinger equation up on the board, just for culture. Let's see. I'm pretty sure the one I wanted to show you. Everything here somewhere. You can say that's the context to all of these things we're studying now. I gotta find, okay, yeah. Good, yeah, so we have a few minutes, we can do this. Okay, so this is called a formalism, and we've been working with precisely these concepts. Suppose you have Ferdinand's equation. And it looks like this. We'll just kind of go I h bar c dt minus h bar squared over 2m del squared c plus u times c. And what is this for? This is for a particle in a potential, right? So u equals u of r, and del squared, you know what this is. So to put this in a form where we can recognize what we've just been doing, what we do is we consider the time dependent. So we consider functions of this form. They're functions of position times e to the minus I e sub n t over h bar. And what happens here is when you take the left side, when you take the time derivative of this, you just get e. Right? E sub n over h bar minus I times I h bar. You just get e sub n. So when you do that, and this is the one we'll study, I'm going to go ahead and raise up here. Because here, this is the one we'll recognize as an operator equation. Okay? So if you do this, you end up with minus h bar squared over 2m del squared c plus u times c equals e times c. So that's an eigenvector, eigenvalue equation. What's the operator? What would the operator be? So we have an operator, we were calling it q hat. So if we have q hat c equals e times c, well, this is the eigenvalue for the energy, right? What's the operator q hat? Anybody see it? What is it?
Factor out the side.
Yeah, so it's an operation, it's a constant times del squared plus u, right? And I gave that example already. A function, is a linear operator, just multiplication by a function. And derivatives are also linear operations. So that is our operator. Not q hat, it is q hat. C equals u times c. Now this one's a lot more complicated than I times d over dt from 0 to 2 pi. It can be, but it doesn't have to be that complicated. Okay. So everybody know del squared in Cartesian coordinates, second derivative x, y, z, right? Summation. What if this were the linear harmonic oscillator? Let's just wing it. If you see it in a book, it'll look different, but if this were the linear harmonic oscillator on the real axis, what would the operator be? Example. This doesn't change, right? The del squared would be, I'll just say d squared dx squared. What would the potential be for the linear harmonic oscillator? Kx squared. Like I said, we're just going to throw in what we know here, right? 1/2 kx squared. And then this would be a differential equation. E times c of x. And it's not going to be easy. Okay? But it is a differential equation. This operator is Hermitian. And you'd go through a lot of work and you'd find a set of orthonormal functions for the harmonic oscillator. And, but, you know, what you want to think of this as being, it's not as simple, but it's the same idea that, you know, we had some differential operator that we found the eigenfunctions for. This one, by the way, don't write this. This one here is the one we did for our Fourier series. This operator is going to have a much more involved solution. But the point is, these functions will be an orthonormal set, and someone found them for you and named them. You look at their properties, right? So if you've been in quantum recently, then you recognize what I'm saying. What about the central force problem? So if this is the quantum mechanical equation for, let's say, a proton and a neutron, what would that be then? I didn't know that one by heart, but I wrote some stuff down for you. So this would be, this was linear harmonic oscillator. And my point is that it's one of these linear operator eigenvalue, eigenfunction problems. That's the point there. And you know, there's a lot going on to get it. In other words, it's one of these. So the other example is going to be central force. And we could say U of R is going to be Q1, Q2 over 4 pi epsilon naught R. Right? And we'll have a positive and a negative charge, and so that'll bring the minus sign to there. But if I write it this way, what coordinates are we going to have to use? Spherical polar, right? The whole, that's going to have radial and everything. So just for fun, I'll write that down. You guys have seen this before. It's 1 over R squared D over dr, R squared D over dr, plus 1 over R squared sine theta D over d theta, sine theta D over d theta. When you study the hydrogen atom, this is what you're going to have. I'm not even done yet. 1 over R squared sine squared theta d squared d squared. So this goes here, right? And Coulomb's potential there goes right there. But again, what you have is, we call this a Hamilton operator. So what you have is H operator C equals E times C. This one's really complicated. And, but again, it's an eigenvalue, you know, it's a linear permission operator eigenvalue, eigenfunction problem. So no matter how complicated they get, they're the same basic thing as our little d over dphi one times I, which is why I consider that the all-time good example. Because here, of course, you can just get lost if you don't realize what you're doing. It's a very complicated, and it's got all the quantum numbers and everything else. Major project. So good. That's what I wanted to show you guys, to give all that stuff context. And Tuesday I'll come in, I'll already know what the exam is, and we'll nail down what we're going to do. I think we'll do one of these Fourier style. We can do a couple of derivatives or something, right? We should be comfortable with that. But I'll tell you that.